All right, so welcome back. Over the break, we finalized the final exam. Remember that it is going to be in person, and it will be on paper. No devices are allowed. For this section, it's going to be on Tuesday, December 16th, 10 a.m. to noon, and it's going to be right here in the same room. Most of your finals are going to be in the same room that you take the lecture in, unless otherwise stated, but I can't speak to everybody like that, all of your courses like that. There will be 33 multiple choice questions. There will be 5 points each, but it's out of 150. That means that if you get all 33 questions right, you will get 9 points bonus, right? So we're just putting those bonus questions in there and grading it out of 150. In the grade book, it'll appear like if you get all 33 questions on 159, it'll appear at 159, and then that will bleed over into other sections. It's going to be comprehensive, all topics. That's from basics to searching and sorting. However, to simplify it, at least for this year, we were just going to stick to C questions because it's going to be the same as in the main section. So we won't have any Java questions on it. There's also going to be an additional bonus that when it's open, I'll announce it. But I will give 15 points bonus, up to 15 points bonus based on the completion rate of the course evaluation. We do take those seriously. I take them seriously, at least. Looking for constructive criticism there. I don't see who, it's always anonymous, so I never see who fills them out, but I want a good response rate. So I'll never know who filled it out. That means that I just take the response rate. So say 75% of you complete it, then that means that I'll take 75%, 0.75 times 15, and then everybody gets those points because I don't know who filled it out and who doesn't. And I'll never know that, by the way. It remains completely anonymous even after I've gotten all of the results. So keep that in mind. Any questions on the final that's coming up? That's it's 2 weeks from tomorrow, basically. Yeah.
Will there be any practice problems so we know what to go by?
So usually it's been in the past. It's been more like what we've done with the other two exams. And so what I've done is I've taken the exams from previous years and done them. And that's what I'll do again. And if we run out of those, we also do Advent of Code. If you've ever heard of that, it's going to be released. Well, I guess it was released today. You can take a look, adventofcode.com, right? Looks like one was released as of midnight Eastern time or wherever they're located. But there are these nice little puzzles, programming puzzles that you can solve. Each one of them is holiday themed. Et cetera, et cetera. So we won't look at this today, but eventually we'll get to it, right? And we'll do some exercises out of that. So we will do exercises, but we won't have multiple choice question exercises. Right? I'm sure that you could probably search a few online or something. But any other questions on the final? No? Okay. Then of course, we'll have a reminder about it. So today we're probably going to end up finishing with searching and sorting, and we'll give a review because it has been over a week now since we've done it. But we'll finish this up today, and then we'll probably go on to, or we'll go into depth maybe on a Wednesday on a little more some other things. But otherwise, you do have your searching and sorting lab and hack this week. Next week is your last lab and hack, and it's on AI. So your lab, you're introduced to AI. You've probably been introduced already, but we walk you through an example of where AI is not going to help you that much because at least when we built the exam, it wasn't smart enough to figure out what was wrong unless you hold its hand and walk it through it. And then on Thursday, the hack. We give you a hard problem that is probably not doable by CS1 students, but if you use it as a co-pilot, as a vibe coder, then you'll be able to complete the assignment. Basically, you're going to be playing Battleship. You have to design a client to play Battleship with our server. It's a one-way Battleship, so you're going to sink our boats. You don't have any boats, and you only have so many shots. Anyway, you're going to have to design and implement that client to do that. And note there that it is due that Friday, so you won't have until the following Monday because it's the last one. We've designed it such that if you put in a full effort, right, then you'll get 20 out of 25. If you win a game, then you'll get 25 out of 25. You have to show that you could actually play the game and win the game. It's very winnable. But the artifact that you'll be handed in addition to the code that's generated, is your thoughts on that process, right? And so that's what we're really going to be looking at, and that's what we want to see. Anyway, that's the end. That takes us to the end of the semester. What I want to do is I want to remind ourselves of where we were. All right, so sorting in practice. Generally, you do not want to write your own searching and sorting algorithms, right? We did that with selection sort, and we saw that it sucked, right? And it's going to involve a lot of copy pasta for different types. You're going to have a insertion sort or a selection sort, excuse me, or a queue sort for integers, one for doubles, one for strings, et cetera, et cetera. If you roll your own, you're going to have to do a lot of testing. You're going to have to do a lot of debugging, right? Don't do that. Instead, use what's built into the language. For C, that's going to be QSort, and for Java, it's going to be sort. Now, it's just historic. There's a historic reason why it's called QSort, because the original implementation was Quicksort. It's not necessarily Quicksort, and even if it is Quicksort, it's not going to be necessarily a fully recursive version of that, because as we've already seen, there's a cost to recursion. However, these built-in functionalities are generic. So what you have is a situation that looks like this, where you have an array or a collection if you're in Java. That's your input. The sorting algorithm knows how to sort, but it doesn't know how to order because it doesn't know what these things are. Is it an array of integers? Is it an array of doubles? Is it an array of strings? I don't know, right? So if it's looking at A and B, it doesn't know which order they go in. Does A go first or does B go first? Do I need to swap them, basically? That's where the comparator comes in. For C, that's going to be a comparator function. For Java, that's going to be a comparator, right? It's a class, basically. And if you give it A and B, it's guaranteed to return something negative if A comes first, something positive if B comes first, and then it's going to return 0 if they are equal to each other. So if you give this thing as a plugin, as input to the sorting algorithm, then the sorting algorithm knows how to sort, it just doesn't know how to order, but then that's what the comparator does. It asks the comparator, are these in order or not? Do I need to swap them? Right? And ultimately, it produces a sorted array or sorted collection out of that process. Right? So as a reminder of how this worked, in C, it was comparator functions. Comparator functions return an integer, right? And they take two const void star pointers. Right? Remember that those are generic void pointers. This is generic programming. If we had put in as an integer here or something, it would only have been good for an integer. And that's not what QSort takes. Right? It does return an integer, though, following that same pattern, something negative, positive, or 0, depending on the relative ordering of those two things. It uses the const keyword because it's not going to be making changes. It's just going to be looking at them and deciding which one goes first. Inside the function, we follow the same generic pattern over and over. We cast the generic void pointers to the types that we're comparing. Then we set up an if-else-if statement to return negative, positive, or 0, depending on the relative ordering. Let's go ahead and take a look at what we've already done. All right, let's jump up here. I lost my code for the honors section, but I think that we pretty much did the same thing, did we not? Yes? We wrote comparators? Yeah, okay. So, for example, CMP int ascending or CMP int descending. What do those look like? Let's jump down here. And let's look at the first one first. All right. Again, the same basic pattern here is that we take A and B, they're const void pointers, they're generic pointers, so we have to force them to become integer pointers so that we can actually compare the values stored in them. We did this, right? Okay, good. At least I had it in my notes that we did this. And so if X comes first, then it returns something negative. If Y comes first, then we return something positive. Otherwise, we return 0 here. Okay. What about a double ascending? Well, we have to basically repeat the entire same code here, but instead we use double. Right? What about descending? Well, we play that game of code golf where we could say, all right, well, I don't need to rewrite the entire thing. I've already got a comparator that does it ascending. I'll just go ahead and call that comparator with A and B reversed. Right? Then positives become negatives, negatives becomes positives, and zeros stay the same. We did books, didn't we? Yes? Okay. So the idea here is if it's by title, you need to force it to become a book, right? And then you reuse as much code as you can. We already have a comparator. It's actually not a comparator, but we have a function to compare two strings, X's title and Y's title, and it has the same exact pattern. It returns something negative, positive, or 0, depending on the relative ordering of the two things. You're going to find that this is true for every single language that you encounter, right? This is the comparator pattern that is supported by pretty much any programming language that I've ever seen, okay? All right, what if you wanted by author, then by title? In other words, you wanted to sort them by author, last name, first name, and then for each author that stays the same, you want them to be listed. You want all the books that by that author to be listed in alphabetic order, right? So what we do is we do a series of comparisons here. I look at the last name. If the last name is the same, right? In other words, it's 0. Then I need to break that tie, like Smith and Smith, but it's Adrian Smith and Bartholomew Smith, right? I need to make a distinction between those two things. So if they have the same last name, then I look at the first name. Now if they have the same last name and the same first name, it's still 0. Then I compare the title and I return the result. What if it has the same last name, same first name, and same title all at the same time? It's the same book, right? So you have a duplicate, or you need to break ties somehow. If it's the same book but different editions, maybe they have different ISBNs, at which point you need to add that tiebreaker in there if you need a tiebreaker, right? So you can always look for something that's guaranteed to be unique, right? Okay. What if it's by year? Careful. This is the difference trick, right? So what I've done here is, well, here's the year and I've just subtracted the year, right? If it's 2025 minus, I don't know, 2020, right? Then this is going to be something positive, right? 0, or sorry, 5, plus 5. I'll emphasize plus 5. But if it's 2020 and then 2025, then this is going to be something negative, right? Negative 5. What if they're the same, 2020 and 2020? Well, guess what? It's 0. This is called the difference trick. Generally, you should avoid this. It's okay in this case because there aren't any books published in the year 2 billion, all right, or negative 2 billion. So all the years are going to be pretty much very, very close. But otherwise, in general, it's susceptible to overflow and underflow. Because if I have like 2 billion and negative 2 billion, then I try to subtract them, then I end up with 4 billion. Can an integer hold 4 billion? Nope. And so consequently, you would overflow, underflow, and you would get the wrong result there. So avoid the difference trick at all costs, unless you are absolutely sure that it's okay. And even in this case, I wouldn't be absolutely sure, right? Because you could be using some, flag value to indicate I don't know what the year is instead of 0 or something, right? All right, so there are our comparators. What does it look like to actually use the comparators? We loaded up all this book data up here, and then we sorted them by year. To do that, we pass in 4 things. Let's go back to our notes over here. The first one is the array that you have elements that you're trying to sort. The second one is the size of the array, the number of elements that you're trying to sort. Then the third one is the number of bytes that each element takes. We're going to use size of all the time. Now remember the reason for this. If it's got an item over here and an item over here that takes 4 bytes and 4 bytes, it's going to have to copy this 4 bytes, move it, and move these 4 bytes over there, and then copy those 4 bytes over there if we want to swap them. If it's that's if it's an integer. If it's a double, it's going to have to be 8 bytes and 8 bytes that are being swapped. If it's a book and it's 40 bytes, then it's going to have to be 40 bytes chunk and 40 byte chunk, and then swap those two things. And that's why it needs to know how many bytes to swap when it actually swaps 2 elements. Then this last thing down here is the comparator function that you're going to be using. That's new syntax. We might talk about that on Wednesday. Probably because it's the H section, we'll talk about it. But basically, this is a function pointer. Pointers can point to integers or doubles or chars, as we've already seen. But they can also point to functions because functions are stored in memory. And this is the way that you can get a pointer to a function. In this case, it's a function that returns an integer and takes 2 const void star pointers, which is a comparator. What is the name of that pointer? Compare is what we've used here. Okay. All right. So here's our example. We're passing in the library, which is what is the library? Oops. Sorry. Undo. All right, there we go. Library is a book star. Right. Does that jive with that? Well, kind of, in that the book will be changed into a void star. It's still a pointer. It's just taking something that points to a book, and now it's pointing to stuff, right? Again, we've got that, I got rid of the diagram, but we make it generic, right? So all it requires is a pointer here, okay? And then let's go back down, sorry, there we go. The number of books, that's the number of books that are in that collection, in that array. The size of book, because it's a bunch of books being sorted. And then CMP book by year, right? There we go. There's my comparator. The way that I passed that in was, I wish I had a back button. I'm sure that there's a back button somewhere. I just don't know where it is. But the way that we pass that in is by the function's name. I'm not calling the function. That would require me to give it inputs. I'm passing the function and saying, this is a thing called a callback. I'm saying call that function over there when you need to know whether or not two things are out of order. Okay? Then we ask the question, what's the oldest book and what's the newest book? Well, if we sorted it by year, where's the oldest book? It's right there at the first one. There's the newest book. It's right there at the last one. Then we've got author and title, right? And then we call CMP by author title there. And then that's the last thing that we did, right? All right, great. Now let's talk about searching, right? Okay, let me come over here and, all right, fine. Let's go ahead and talk about searching with bsearch, okay? Where is bsearch? Darn it. All right, so let's go ahead and search for it, bsearch, C. I'm just pulling up the man pages here. There we go. I don't want that. Yeah, okay, that's good enough. No, that's not good enough. That's terrible syntax there. That's the one I want, right there. All right, so let's bring it over here. Well, first of all, what do you think bsearch stands for? What does the B stand for? It's a binary search implementation, okay? And here is its signature. Let me go ahead and clean that up a little bit here. Oops. So const void key, const void ptr, size, count, size, and then a comparator. Oh, come on. Why is this not working? Oh, I need to go into full code modes here. So signature, and there we go. 1, 2, 3. And does that look better? There we go. Oh, no, it doesn't look better. Let me go down to the next one. Okay, there we go. And I'll realign everything there just to make it look nice. All right, so hopefully this looks pretty familiar here. These four are the exact same arguments as you give with qsort. PTR is the base, and let me rename that to be consistent. Base, right? The count is number of elements, the size, and then the comparator there. That's exactly the same as we have up here. Let me say that this is C. There we go. That's going to look better. Okay. All right, what's the difference though? Well, there's one difference right there. With qsort, was the array designated as const? Nope. It is const down here. Why do we have that difference? Why is it not const up here with qsort? Because it's changing it, exactly. It's going to take all your stuff and it's going to rearrange it. But if you're just searching, are you going to be changing the array? Absolutely not. So the array is now const. All right? It only searches. It does not change it. Right? The other difference here is it also takes a new first argument. That is key. Now, tell me about that key. Oh, sorry. There we go. It's const, so are we going to be making changes to it? No. But it's a void pointer, right? So in other words, it's a pointer to a thing that is your key, right? So it's also a generic void pointer, but it needs to match the type of your array. All right. In other words, it must be the same type as the things you are searching. If you have an array of integers, then that's got to be a pointer to an integer. If you have an array of doubles, then it's got to be a pointer to a single double. If it's an array of books, then it's got to be a pointer to a book. Okay. All right. So my first question here is, if we already have the key, why are we searching for it, right? For example, if I had an array, 10, 20, 30, 40, 50, 60, I have a pointer to 40, right? I already have 40. Why do I need to search for it, right? Well, one, I need to know, is it actually in the array or not, right? Two, there's something called it's not necessarily a surrogate key, but we'll call it a dummy key, right? What if I'm searching for a bunch of books? I'm searching for a book with a particular ISBN, XYZ123, right? I don't have any of the other data. I'm just searching for the book with that ISBN, right? If I had all the other data, then yeah, I agree. I wouldn't need to search it all. But I want to know who its author is. I want to know what's its title. I want to know what's its rating, right? But I only have a key to find it. I only have an ISBN to find it. That's how we're actually going to end up searching, okay? So let me come back over here and let's go ahead and, do I have an array of integers? Let's go ahead and demo for integers, okay? So let me go ahead and create an array of integers, right? ARR, right, is equal to 5, 8, 3, 4, 5, 0, 9. Right? All right, now my first question is, am I going to be able to binary search that thing? What does binary search require? Do you remember? What's the assumption? You can jump to that it's sorted, right? Because you can jump to the middle and say, that's the thing I'm looking for, or no, I need to search in the left half, or I need to search in the right half, right? So am I going to be able to binary search that array? Not this one, right? Let's see the consequences of that, though. How many things are in there? 3, 4, 5, 6, 7, right? There we go. So B search, right? I need a key. And I'll leave a question mark there for a second. But otherwise, help me out. How would I end up searching that array? The next argument is going to be the array that you pass in, that you're searching. So ARR in this case. The next argument is the size, the number of elements in the array. In this case, I put it into a variable called n. Then I need size of int, because it needs to know, am I comparing this 4 bytes, or am I comparing this 4 bytes, or am I comparing these 8 bytes, or 40 bytes, 40 bytes, 40 bytes? And then finally, the comparator that you want to use. CMP, what was my integer comparator? There we go. We'll assume that it's in ascending order there, right? And come back up here. There we go. All right. And now I need to answer this question of, well, how do I give this key? Let's go ahead and go with int key is equal to, say, I don't know. Let's go with 8. I'm going to search for 8. Should that be a successful search? Yeah, it should, right? But how do I pass that in to B search? Can I just do key? Nope. What is it assuming? It's a pointer, a generic void pointer. So if I've got a regular old variable, how do I get a pointer value out of that? Ampersand. Oops, ampersand in front of it. There we go. Now that doesn't tell me where it is. Right? So let's come back over here and see, oh, now I'm actually returning something. Whereas with QSort, it wasn't returning anything. We're now actually returning something with bsearch. What is the thing that we are returning? Upon a successful search, for a successful search, full search, it returns a pointer to a or an element that matches the key, right, according to the comparator function, right? Now, why did I emphasize an? What if there are multiple 8s? There are 5 8s in there. Which one does it return? Right? I don't know. One of them, right? It's up to you to find out if there are multiple ones, and you're going to have to write your own searching algorithm to find them all, right? So for an unsuccessful search, what does it return? Well, what's the only thing that it can return if the return type is a pointer? ULL, null, right? So let's come back over here and capture that value. Int val, right, is equal to bsearch. Okay. Now you can, of course, go ahead and force it to become an integer value there. Right? I generally do that, or you could leave that off if you don't want that. But basically, it's like calling malloc. You cast the generic void pointer to the appropriate type. And let's see if this actually worked. So printf val, here, I'm going to need an if-else if statement here. If val is equal to null, I'll say printf could not find key equal %d and the line and key. Right? Otherwise, it's not null, and so we know where it lives. So we can say printf found %d at memory location %p, right? And we'll say that we found the key at val. There we go. Okay. And I'm in the wrong directory. Again, I lost the code. I don't know why. gcc book.c and demo.c all together. There we go. And let's run this. All right. So there's a bunch of book stuff, right? And it could not find the key 8. Right? It returned null. Now, why was that? How does binary search work again? It goes to the middle, sees 4. Where should 8 be if it's sorted? In the right half of the list. Over here, it was in the left half of the list. So it goes and recurses over here, and it recurses, finds, it doesn't find what it's looking for. So the consequence of this is that it's not going to be a valid search if it's not sorted. So let's sort it first. I'm not going to manually sort it. Let's go ahead and sort it right here. Qsort. What do I pass into Qsort? Remember, it's the exact same 4 arguments. Right? So there we go. Let's see if that worked now. GCC this and a dot out. Now I do find 8 at memory location, blah, 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 blah. Okay. What if I had used a different comparator? What if I had used descending instead? GCC this and run this. Could not find key at 8. Why? Well, what if it were descending, where would 8 be? Right where it is right now, right? On the wrong side. Right? So the takeaway here is if you are going to use bsearch, right, it has to be sorted, and it has to use the exact same comparator as was used to sort it. So if I could go descending on both of them, and I could successfully find it again, right? But it has to be consistent. That's the takeaway there. Okay. All right. For complex objects or complex types, that is structures, you can use a dummy key, right? So for example, say that I have an ISBN, right? Char, let's search for a book. Let me go ahead and open up the data here. Do I have an ISBN? There's an ISBN. All right, there we go. All right, you know what? Let's search for the title instead. All right, char title. All right. I'll do it like this. Title is equal to that. Let's search for Polybius, or however you pronounce that. Okay. It was obviously not an audiobook because I don't know how to pronounce it. So Polybius, Polybius. Let's just go with that. Right now, when I search through my books, my library up here, right, I'm searching a bunch of books. Do I have a book here though? Is that a book? It's just a title, right? A book is many more things, so I'm not going to be able to search for it, right, by title. First of all, let's go ahead and Qsort it by title to make sure that it is actually sorted first. So library, num books, size of book, right? And then finally, what is my comparator for title? If I were consistent, it'd probably be CMP book by title. Yep, CMP book by title, CMP book by title, right? There. Now, if I were to try to search for that book result is equal to bsearch. What is my key in this case? Now remember, the rest of this is just a copy pasta, right? Exact same 4 arguments there, okay? But in this case, what's my key? If I tried to do this, if I said title, right? Am I going to find it? Let's find out if I do. If result is equal to null, I'll say printf no such book. End the line. Otherwise, else printf. And how do I print a book here? I think I've got a print book. I'll just do this here. There we go. So there's the book string. And I need to pass in the book. So it's going to be result. And then I print it out. Yeah, that's all I need. Right? Printf found the book. There we go. There. So let's see if this works here. GCC and a dot out. Segmentation fault. Right? What happened here? What is library? What type is library there? Let's go back up to it. It is an array of books, right? Let's go back up here. There we go. And basically, I'm certain we sometimes use the terms needle in a haystack. You're searching a haystack for a needle. Well, the haystack and the needle have to be the same types, right? I'm searching the haystack of books. My needle needs to also be a book, right? Is title a book? Nope. So what I need to do is I need to create a book with that, with just the title defined. Do I have something to do that? Do I have a create book function? Yes, I do. Right? All right, so let's go ahead and create a book key, right? Book star title key is what I'll call it, is equal to create book. Now, what were the things that I have to pass in? Let me go ahead and dual screen this over here so that I can look at it. All right, there we go. Create book. Well, it requires an ID. Do I know the ID? Nope. It doesn't matter. Just go ahead and give it a dummy ID, 0. Do I know the title? Yes, title. Right? That's the thing that I'm searching for. Do I know the author's last name, the first name, the ISBN? Nope. I mean, that's why I'm searching for the book, because I want to know those things. So what could I pass in there safely? Either null or an empty string. Empty string, empty string. I don't know how safe null is. It depends on our implementations of what we did, right? And then rating, 0.0, doesn't matter. Empty string, year, 0, and empty string. There. Now, does it matter that any of that stuff is defined? No. The only thing that my comparator here, CMP book by title, is going to be looking at is the title. As long as that title is set, then I'm good to go. Right? Let's go ahead and pass in now that actual title key. Title key. There we go. Now I'm comparing apples to apples. Before I was comparing apples and oranges. Right? I was comparing a string to a bunch of books. Now I've got a book and I've got a book and a collection of books here. GCC this, run it again. And now I did find it successfully there. Who wrote it? Colin Armstrong. It was released this year, and it's got middling reviews, right? 3.39. Right. I'd agree with that. Right. All right, any questions? No? Then let's look at the same thing in Java over here. Actually, let's remind ourselves, let's do a quick review here in Java of what we were doing. I do have all the code here. All right, so where were we? Oh yeah. Creating comparators. So remember collections.sort. Well, if you've got just a regular old built-in like integers or strings or whatever, right? Then you can use the collections.sort and it'll do it in the natural order. But if you want something to say descending, then you need to create a comparator. A comparator, the way that I've done it here is this is an anonymous inline class here, right? What I've done is I've created a new comparator. And it has one method that you need to implement, comparing A to B. Well, if they're built-in types, what you can do is you can use the compare to method. And here I've reversed it, B compared to A, so it's going to be in descending order. And then ascending, what you could take any comparator and then go dot reversed on it, and it'll return a new comparator on that. We did that for integers, then we did it for books. If you want to do it by title, then you can go ahead and get the string of the titles and then compare the titles and return that value. Or you can do the more modern way of doing this is to chain build these things. Comparator, you can say comparing, and then you can use this syntax right here. This is a colon syntax. This is a method selector operator. The book, if it you go ahead and get the title. In other words, compare it by the title. But I want it reversed, so dot reverse. You can chain that as many times as you want. I want to compare it using the rating, reversed. Then comparing the title, reversed. Then comparing the author. And that's where it failed last time, right? Well, actually, no, it failed at first because author was, or where's my author class? Where's person? There's person, there we go. What we did to fix that is we made person comparable to another person. How do you compare people? Well, if they have the same first name and the same last name, then they're the same person. And so that's where we left it off. I have to compare this person to that person. So compare this person to that person, dot, dot, dot. How are we going to do it? Again, last name, first name. If there were other options, like in real life, how would you compare, oh, that person is the same person, right? If it were in the context of UNL, what would it be? Your NUID, right? If it were in the context of US taxpayers, social security numbers, right? If it were in the context of books, I'd say ISBN, right? So we don't have that data though, so we're only going to be able to compare the last name and the first name, right? So how do we do that? Right. Well, let's go ahead and compare this person's, this dot get last name, or dot last name. Let's compare to that person dot last name. Okay, oops, result is equal to. That's why it's not compiling. Right. Now, if they have the same last name, right, if the result is 0, then what do I need to do? I need to look at their first name. Result is equal to this dot first name is dot compare to that dot first name. Okay. If they have the same first name and the same last name, how do I break ties? In this case, I don't have enough data to say. So I'll just return result. There. That's how I can make a class comparable. I think one of the last questions we had, it was been over a week, was, well, what if we do that with book, right? And now that's why it's not compiling. So let's go ahead and add the unimplemented method here. And I'll ask you, how do we implement it? I want to compare this book to that book. How are you going to do it? Let me come up here and show you. There's the data. Choose the data that makes that orders 2 books. Title? Maybe. I'm sure that there have been plenty of books with the same title out there, though, right? By different authors. It's not common, but it happens. So I don't like title. Is there something here that makes it absolutely comparable, though? This is something we call a total order, right? That no matter what 2 things you have, it either A comes first or B comes first. It's not the same. They're not the same book, right? That it's always comparable somehow, right? So, is there something in here that makes it absolutely unique? ISBN. Okay. So return this dot ISBN dot compare to that dot ISBN. Now, the reason that you would want to do this is if you want a natural order. That's a natural order. We're guaranteed that the ISBN is always going to be unique. Okay. If this were tied to a database, however, I would probably use whatever database key is being stored, because this is what's known as a natural key, right? And we don't control it. Do you think in the history of ISBNs they've never screwed up and issued the same ISBN to 2 different books, or issued 2 ISBNs to the same book, right? Nope, it happens probably. Just like social security numbers, it happens with them. Just like NUIDs, they screw up all the time. Not all the time, but it's not uncommon, right? I don't want that to screw my data up. I don't want that to screw up my application. So what I would generally do is I would use the database key instead, because I control the database. We'll talk about that next semester in CS2. The other reason that you might not want to do this is because, well, it locks you into one ordering, right? You're going to have to make comparators anyway, right? If I were to naturally order those books, do I have books already? I'm not loading up the books, so I can't do it, unfortunately. But this is how you build comparators, right? Then if I were to say collections.sort, and if I had a library here right now, I could do something like this now that it's comparable, right? I can at least get it to compile by showing you, let's see, a list of books called library is equal to null. Right? There, it'll at least compile now, right? Whereas before, if it was not comparable, it would not let me do something like this. Let me show you. I'll go over here to book and I will take out that implements. Right? There we go. All right. Now demo breaks over here because that has no natural ordering. Right? It does not have a compare to function. Let me go ahead and restore it over here. Right? There we go. All right? And over here now it's perfectly fine with that. It'll use the ISBN though as its key to sort it. Right? Ultimately, though, the ISBN is not very useful data for a book, right? Yeah, it's good for sorting book, for storing books or whatever. But ultimately, we're interested in the title or the author or the rating or something like that. And so ultimately, what we have to do is create these comparators anyway. Right? This this comparable interface, it's only good for one thing, and that's it. Once you've defined that one thing, there's no redefining it. The only way that you can redefine it is by using these comparators outside here. Right? And then collections.sort, library, and then CMP book foo, right? Because I'm not even sure what we were thinking of last time. I just picked random things there, right? All right, well, with the last 10 minutes here, what about binary search? Collections.binary search, there it is. And guess what it takes? It takes the library, the thing that you're searching for. It takes the key. And then finally it takes whatever comparator you're trying to search for, right? Let's go with that, like this one, right? Same thing here. It requires it to be sorted in that order. So collections.sort, library, CMP, book descending. Right? Now what about the key here? Again, you need a dummy key. Right? And in this case, we can actually do something different than what we did in C. I want to be able to define just the title. Remember that we can have multiple constructors, right? So I'm going to go ahead and create a constructor here that I don't want to have to pass in dummy crap all over, right? So what I'm going to do is I'm going to have just the title here, right? Okay? So that I can create this book. Let's go ahead and create a book. Polybius is equal to new book and Polybius. There we go. With just the title defined. And then I can use that as my key. No pointers in Java, right? So I don't need to, an ampersand. I don't need to make sure that it's a pointer or anything like that. Now, over here, we need to actually finish this out to get it to work. I'll bring in the library next time and we can demo it and make sure that it works. But otherwise, how do I define it? This dot title is equal to title. What about the rest of the stuff? What about setting the ID? What about setting the title, the author, et cetera, et cetera? You don't need to do it here because there will be default values. The default value for integers is, guess what? 0. The default value for types, for classes, is going to be null, right? The default value for a double is going to be 0.0. And I don't have it here, but the default value for a Boolean is going to be false. Right? So there are default values there, but it's best practice to actually set them all explicitly. Let me go ahead and do that. Copy all that, paste all that, and replace all these. 0, null, 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 0, null, and 0.0. Right there. Oops. 0, sorry, there we go. Right. A lot of copy pasta though, right? So here's another trick. I'm going to call that other constructor with all these default values. Right? That other constructor will take in 0, title, null, 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 or no, not null, 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 0.0, null, and 0. All right? Now how do I call that constructor? How did I refer to myself in this class? This, right? So how do I call that constructor? Also this. Right? Get rid of that. All right, let's see, it should be 0, title, null, null, 0. Oh, and then I need a null, and then 0. Oh, and then null again, sorry. I missed one, date red, in my copy pasta. There, no repetition at all here. Right? This ends up calling that constructor up there. I'll prove it to you by jumping to that constructor. Right? So I'm just passing off these default values and then passing off the only one that I actually care about there with the title. Okay. This is actually the best way about going about doing it. Okay. Any questions? Oh. All right, so pretty straightforward for your lab and your hack this week. We'll go ahead and finish this. There's just some miscellaneous stuff that we'll take care of on Wednesday. After we're done with that, I'm not going to lecture on AI at all, right? I mean, we're not going to get into how LLMs work or anything like that. The lab and the hack walk you through the basic steps on what you should be doing when you use it. But otherwise, I guess on Wednesday and Friday, we'll start a review. I'll bring out old tests then. Right? Or we'll do Advent of Code. I'll see how hard it is this year. Right? How many people have done Advent of Code before? All right, you have? No? All right, it's pretty fun. It's been going on for over 10 years now. So if you want to go back, 2015, I got all 50 of my stars there. Right? You can see I don't do it every year fully, but sometimes I'll do it for a review or something. I don't know what 2025 looks like, but let's look at last year. Okay, so you're given like two lists of numbers here. The lists aren't very similar. Maybe you can find out, pair up the numbers and measure how far apart they are. So pair the smallest number in the left list with the smallest number in the right list. Then the second smallest left in the left with the second smallest in the right. Right? That's very probos of what we're doing right now. Why? How would you go about solving this? For example, the smallest number in the left list is 1. The smallest number in the right list is 3. So the distance between them is 2. Right? If you go to the second smallest number in the left list, it's 2. The second smallest number in the right list is 3. Right? This right list up here. Right? And the distance between them is 1. Right? So how would you go about doing this? You'd sort them, right? And then once you've got them sorted, all you need to do is go through each one and take the distances between them. So if I would highly recommend that, just for fun over the break or something, doing something like this. They do get harder. That one was easy, right? This one, I think I did this one the other day just because I was bored. Okay, yeah, this one was really good. So you're given a number, and then you're given a bunch of numbers. And you're asked, well, is there any combination of add and multiply of these other numbers that equals this number over here? So you have to try all combinations. For example, this combination over here, there would be 1, 2, 3 operators. You'd have to try all possibilities. So you could be plus or multiplication, plus or multiplication, plus or multiplication, right? And then, so that's 8 possibilities for this one, right? For this one line right here. And you have to see if any of those possibilities sums up to 292, right? It was actually really easy because I used recursion, right? You're just basically probing. What you do is you recurse and say, well, what happens if I use plus here? Then it recurses, what happens if I use plus here? Recurses, what happens if I use plus here? Then it backtracks. That didn't work. So what happens if I use multiplication here instead? Right? And then you backtrack all the way. You end up trying every single possibility. Right? Unfortunately, the actual, so they're very, very Python-centric because these numbers are too large for C. So we won't be doing it in C. But in fact, we probably won't be doing this one at all. But thankfully, I started out in Python knowing that they were probably going to be way too big. But so some tips if you're going to do this, do it in Python just to learn a third programming language. And because they're going to be large numbers. And it's also going to be easier to read in the input. And 2, they get harder day by day. And every day you have 2 parts. Right? This is how you get 2 stars. The first part is generally easier than the second part. The second part throws you for a loop and says, okay, well, that was easy, But now what happens if we do this thing over here? Right? So if you're looking for more practice, I would say go to Advent of Code. Go back to 2015 because they were much, much easier in the first year. All right. So I'll bring you our finals next time, or Wednesday, Friday, whatever.